Thank you. I thank the organizers very much for the opportunity to contribute to this event in honor of Eugene and Reyer. I particularly appreciate the opportunity to give a talk without either traveling or going on Zoom. In any case, this work is joint work with Indranil Biswas, Jacques Hurtubise, and Sean Lawton, and our paper is on archive and accepted for journal in symplectic geometry. So I will go through general material on character varieties, studying their Poisson structures, studying their behavior under maps between surfaces meaning oriented to manifolds, sometimes with boundary, and the construction of these Poisson structures, and procedures for changing from one surface to another, capping, and finally I will talk about gluing via symplectic quotients. That part relies on quasi-Hamiltonian manifolds, quasi-Hamiltonian spaces. Okay, so no, so it will work back, but it will not go forward. I just put new batteries in it, so. The clicker is not working. What did? Yes, I know. I had done that. Okay, so thank you. Thanks very much. Okay, so let's suppose that we have two surfaces, possibly with boundary. And G will be either a reductive group, meaning complexification of a compact Lie group, or it could be a compact Lie group. So I will denote X is the representations of the fundamental group into G divided by conjugation. Same thing for the surface sigma 2. So these spaces are Poisson manifolds. If the boundary is empty, then they're symplectic spaces. They do have singularities, but I will I won't be actually talking about the singularities. I will confine myself to the portions which are actually smooth manifolds. So this symplectic structure was developed by Atiyah and Bott independently by Bill Goldman. So let's suppose first that sigma 1 is just a subset of sigma 2 and F is the inclusion map. So this gives you basically a pullback map from X of sigma 2 to X of sigma 1. So why does it work when he does it and not when I do it? Sorry?
Well, there's some button that you press that makes it a plus hand instead of.
Oh, so. That.
I'll just sit here. You tell me when to advance.
Sorry. Okay. So F star. This is just maps from representations from the second surface to G into representations from the first surface to G. Strictly speaking, this isn't a map of character varieties, but because this map is equivariant with respect to conjugation by G, it gives you a map of character varieties. Sometimes we will denote a surface with genus G with n boundary components by sigma n comma G. And then we'll write x of sigma n comma G as x sub n comma G. And we will show that this map is a Poisson map. Question?
Yeah, so the surface one inside surface.
Yeah,
two, right?
that's the first
So
example.
should we be thinking this is full map?
Yes, exactly,
Full
exact.
map, not
Yes,
push-pull,
yes,
right?
yes, yes,
And what is phi? Is this a map
Uh,
on the quotients?
yes. Well, induced on the character varieties.
On the character,
Yeah.
like the whole
Yeah.
thing from Taiwan, I guess I'm struggling to.
Okay.
get to the-
Okay.
Taiwan actually means Taiwan of the second surface.
Yeah, yeah.
Okay, thank you. Lisa.
Okay. Okay, so. Okay, so suppose that the two surfaces have the same Euler characteristics and both surfaces have at least one boundary component. Either both of them have at least one boundary component, or neither of them has any boundary components. In this case, the two character varieties are isomorphic. So this breaks down into three cases. First, when both surfaces have one boundary component, and the second case is when both surfaces are closed, no boundary components. And then there is the third case when at least one surface has no boundary, but not both. So we have to confirm that in that case, they are not isomorphic. So in the first case, both fundamental groups are of the same rank, so the character varieties are isomorphic. The surfaces don't need to be homeomorphic, but they must be homotopy equivalent. In the second case, the fact that the Euler characteristics are equal means that the surfaces are homeomorphic, so their fundamental groups are isomorphic. And hence the character varieties are isomorphic. No, these are two closed surfaces with the same Euler characteristic. Well, all you know is that two surfaces have the same. I mean, by classification of surfaces, you would be able to conclude that one is contained in the other.
So the map, that was just a map between them?
Well, it's inclusion. Well, I mean, we're not talking anything about complex structures or even.
And they're connected.
Yeah, they're connected.
Same one.
Yeah,
It's the same thing.
yeah, yeah. So next slide. Yeah. So I don't think I will go through the details of excluding the case where one surface has a boundary and the other does not. So in the third case, the Euler characteristics are equal, but the character varieties are not isomorphic. So I think we'll just go on. Okay, finally, suppose that two character varieties are isomorphic. In those cases, the surfaces have the same Euler characteristic, and either both surfaces are closed or neither is closed. This really boils down to what was on the previous slide. If the two character varieties are isomorphic, then their dimensions are equal. Suppose one has non-empty boundary, but the other one doesn't. Yeah, this is fairly technical argument involving, here I am talking about the case where you have reductive group G, which is the complexification of a compact group K. And so there is a way to show that in that case, you can't have one with a boundary and the other without. So I should say that if two character varieties are isomorphic, it doesn't automatically follow that the fundamental groups are isomorphic. A simple example is one group is Z2 and the other is Z3. Both of these have the same character varieties as representations into SL2C. In both cases, the character varieties are sets with 2 points. So in both cases, of course, the identity is sent to the identity. For Z2, the non-identity element is sent to minus the identity matrix. For the Z3, the two non-identity elements are sent to 2 roots of Z cubed equals 1 in SL2C. These are, so there are 2 possibilities, but they are conjugate. So up to conjugation, there's only one possibility that is not the identity. Okay, so here I am restricting to the case of reductive group complexification of a compact group. So in local complex coordinates, which I'll call Z sub I, the Poisson vi vector on the character variety can be written as sum of Aij partial Zi wedge partial Zj. So these are basis elements which have to do with the coordinates that you've chosen on, coordinates come down to coordinates on the group, and Aij is a function of the Zi. This is work of Bill Goldman and Sean Lawton. So if alpha and beta are base loops in the surface sigma 1, we'll write these as bracket alpha and bracket beta in the fundamental group. So we can assume that these base loops intersect in transverse double points. And I'll write alpha cap beta as the set of double point intersections. This is a finite set. And the intersection number at these points will be epsilon alpha beta. This is plus or minus 1. And we'll write a representation as script R. So here, let's let F be a class, sorry, whoops, I did not mean that. Oops, what did I do? Oh, that was one. F is a class function. In other words, it's invariant up to conjugation. So let's let A be an element of the group, and associated to our function f, there is of our function little f, we write a function big F. This is now a function from G to the Lie algebra of G. So it's defined in terms of the derivative of little f. And this is in fact an element of the Lie algebra. So for example, in the case, I think that for GLNC, SLNC, you use trace of A. For the compact groups, un, sun, and little f is the real part of the trace. This function, big F, is a minus a inverse over 2. And that is, in fact, an element of the Lie algebra. So Goldman and Lawton write the Poisson bracket as Poisson bracket of these two functions, f sub alpha and g sub beta, as the inner product of f of r alpha beta, r of alpha, and g of r of beta. The inner product is just the killing form on the Lie algebra. And you're summing over the points where alpha and beta intersect. So Goldman proved famously about these functions that if alpha and beta do not intersect, then the corresponding functions Poisson commute, which would be obvious from this formula because there are no points in this sum. But if they do intersect, then you have a contribution from each point. Oh, it did work. Okay. Okay, so if we have maps between surfaces, let's suppose Q from sigma 1 to sigma 2 is a continuous map. We're no longer in the case where sigma 1 is, Q doesn't have to be the inclusion map, which was what we were talking about earlier. In this case, there's an induced homomorphism of fundamental groups, and there's a continuous map between the representation spaces, and this descends to the character varieties. So this gives you a map from x of sigma 2 to x of sigma 1, character varieties. Goldman proved in 1984 and 1986 that if Q is a continuous map between compact orientable surfaces and it preserves transversality of base loops and it preserves double points, then the induced map of coordinate rings this goes from C of x of sigma 1 to C of x of sigma 2. This is a morphism of Poisson algebras if Q preserves orientation, and it's an anti-Poisson morphism if Q reverses orientations. So the Poisson bracket was what I wrote on the previous slide. This was given by Goldman in 1986. This is the case where no boundary components and genus bigger than or equal to 2. So for genus 1 and 1 boundary component, Goldman found the bivector in 2006. And for surfaces with no boundary and a torus, this case was worked out by Adam Sikora, 2014. Sean Lawton proved the case where there are surfaces with boundary, and again, Lawton also contributed to the case where n equals 1. So a torus with one boundary component. And Goldman also found the bivector for So this is where you have a sphere with four boundary components, and also a torus with two boundary components. Yes, question.
Can you explain a little bit more about the transversality of what does that mean?
The map sends the map will this is a map between surfaces. So if the map will take one loop to another loop in the other surface, and if the loops intersect transversally, then the image loops also intersect transversally. It doesn't collapse one loop to something that doesn't intersect transversely.
This sounds very much like either local diffeomorphism or perhaps locally embedding.
Yes, well, certainly those things would give you those.
Transversality has to do with tangents.
Yeah,
and
yeah.
Would be at least possible to ask whether these are exactly the same things that are locally different.
It may be. I can check. Well, you can I don't want to fast forward to the reference to. I could. Why not? Let's see. References. I'm coming back. Okay. Whoops. Goldman. So it is. This is the 2006 paper, and that is the 1986 paper.
It's not unreasonable for us to simply think of the guys that are either locally diffeomorphisms or local.
No, that's not at all. That's not at all unreasonable. Yeah. Okay. Yeah, and there's Sean Lawton's paper, and Sikora's paper is on the next slide. Whoops. What did I do? Yeah, Lawton's paper and Sikora's paper. Okay. So. Okay, so that was where I got to. So now let's assume that the surface is an open, smooth manifold instead of a manifold with boundary. And G is either compact or reductive. Fix a base point. And R is script R, as before, a representation. I'll say that the representation is reductive if the Zariski closure of its image in G is a reductive subgroup. This condition is always satisfied if G is compact. So XNG is the quotient by conjugation of the space of reductive homomorphisms of the fundamental group of the surface up to conjugation. Yes. And another definition, a G connection on sigma 1 is a smooth principal G bundle equipped with a connection. So E is a vector bundle over the surface, which is associated to, associated to the principal. E sub G is a principal bundle, so E is a vector bundle that is associated using the adjoint representation. So Poincare duality tells us that the tangent space of the character variety is the compactly supported first cohomology of E, so over sigma. So there's a natural homomorphism from the cotangent bundle to the tangent bundle, or equivalently a two-form on X of sigma. this is given by taking the inner product of a one form with a compactly supported one form on sigma. And that gives you a compactly supported two form on sigma. And then you integrate that over sigma. I'll denote this homomorphism by capital theta. So this goes from the cotangent bundle to the tangent bundle. Or you could write it as a section of the space of two forms of X and G. And in the case where sigma is a compact oriented surface, no boundary, then theta coincides with the symplectic structure that was constructed by Atiyah Bott and Goldman. So suppose that sigma 1 is embedded as a connected open subset of sigma 2. That was the situation that we started off with. Then the restriction map from sigma 2 to sigma 1 gives you a map that we'll call phi. This goes from the character variety of sigma 2 to the character variety of sigma 1. And apologies for having previously used beta for a loop in a surface. I will now use beta for a map of the first cohomology. In other words, the tangent spaces. So this just comes from restriction from sigma 1 to sigma 2 to sigma 1. And there's another map of, in the other direction, you can think of this as push forward, but this is where the forms have compact support. So basically, the map beta is just the differential of the map phi. This map results from pulling back one forms under the inclusion map from sigma 1 to sigma 2. The map gamma really corresponds to the dual of that map. And this results from pushing forward compactly supported forms, one forms from sigma 1 to sigma 2 under the inclusion map. So our result is that this map is Poisson. What we mean by a Poisson map of two Poisson manifolds is, suppose theta sub A and theta sub B are the Poisson structures. So it just means that df, really this should be written as df composed with theta sub A is isomorphic to theta sub B composed with df. So that's what we have to check. In this situation, we can have the maps that we previously had, which were inclusion maps. We could also have a covering map or even a ramified covering map from one surface to another. We define a map psi, which goes from the character variety of sigma 2 to the character variety of sigma 1. This is obtained by pushing forward the fundamental group under the map little phi from sigma 1 to sigma 2. And we show that this map psi is a Poisson map. This uses that the map deep psi sends a cohomology class to its pullback under little phi. And the map that is dual to d phi sends a compactly supported one form to the sum of its pullback over inverse image points under the map little phi. This new differential form is also compactly supported. So what do we mean by capping? Suppose that sigma 1 is a two manifold with boundary. Let's let sigma 2 be a two-manifold obtained by capping off the boundary components. So suppose we started off with a two-hole torus. You could just close the holes by adding a little disk. So this case, the map phi is an injection. The image is the inclusion, is the union of a family of symplectic leaves. There's something else you could do, which is to cap it with a cylinder. So here you're just gluing the ends of the cylinder to the two components of the boundary of the surface. This produces a surface with two less boundary components, and the genus is increased by 1. So that these two character varieties have the same dimension. Yeah.
Is this one Poisson and this one symplectic?
Well, the one on the left would be Poisson because you have boundary. So here is another case where you're capping with a K-hold sphere. So here we have 3 boundary components, and we're sealing them off with the boundary components of, well, this is a pair of pence, a 3-punctured sphere. So the resulting surface has K less boundary components, and the genus goes up by K minus 1. In this case, the map phi is not surjective. You can check that by just checking the dimension of the character varieties. The previous case, you couldn't check that because, in fact, the dimensions, in case B, the dimensions were the same. So another case is capping one boundary component with a genus 1 curve, like so. So we'd started with a genus 2 surface with 1 boundary component, and then we glue a once punctured torus to that. So in that case, if G is semi-simple, then the map phi is surjective. This is not necessarily the case if G isn't semi-simple, because basically you have to, you end up with, in order to glue something to the once punctured torus, you end up with something that has to be in the commutator subgroup. And a semi-simple group is a group where G is equal to its commutator subgroup. That is not the case if the group is not semi-simple. And so you might not get that this map is surjective in that case. Then there is a case where you cap with an n-punctured genus 1 curve. So this illustration is where we have 2 boundary components, and we're gluing a 2-hole torus to it. So in this case, the map phi is surjective and Poisson. So finally, I want to say something about how this picture can be treated using quasi-Hamiltonian spaces of Alexeyev, Malkin, and Mainrenken. So I will briefly describe those spaces. So these are spaces that are equipped with a 2-form. They're equipped with a group action and a 2-form. The 2-form is actually neither non-degenerate nor closed, but it produces, this group action and the 2-form do produce an equivalent of a moment map, which can be used for constructing symplectic quotients. In any case, one example of a quasi-Hamiltonian space is the double, which is just the product of two copies of the group. And this has an action of G cross G, just left multiplication, right multiplication. I will also talk about what's called the internal fusion, which is, the space is the same, but what's left is one group action, which is basically the adjoint action. So this is the internal fusion of the double. So the action of G cross G on the double is just by left respectively right multiplication, and that's one of the group actions, and the other one is right respectively left multiplication. And the two form on the double is, so here we're using A and B to be points in G cross G, and theta is the Moret-Cartan form. Write that out. Yeah, so theta, if you were using A as your coordinate on G, then theta would be written as A inverse dA. The internal fusion, you only have one action, which is the adjoint action, and the two form looks like this, starting with the Moret-Cartan form. So the Q Hamiltonian space obtained from the product of R copies of the double and G copies of the internal fusion of the double. This now has a quasi-Hamiltonian action of G to the R plus 1. So R of the actions are from the adjoint action that corresponds to this part, the double, and the G part, you have the action for the double, so left and right multiplication. And this space is equipped with a two form that plays the role of symplectic form. The two form I talked about already, and the moment maps come by taking coordinates and their images under the adjoint map, adjoint action. Whoops, that's not what I meant. So here we're using the notation A and B to refer to a 2G tuple of elements of the group. And U and V, similarly, this is a 2R tuple. And the commutator means AB, A inverse, B inverse. Sorry, that should be G, not H. So to form a Poisson manifold by gluing two boundary components of a connected surface, we set the values of the moment maps corresponding to these two components to be equal, and then we take the quotient by the diagonal action of the group. So this corresponds to gluing the two boundary components together, or gluing on a cylinder. To form a Poisson manifold gluing boundary components of two different surfaces, we set the moment maps on the two Q Hamiltonian spaces to be equal, and then we take the quotient by the diagonal action of the group. So this is how it looks if you're gluing together two one-hole torus, two copies of the one-hole torus. And you can iterate this procedure, and if all boundary components are glued together, you recover ultimately a symplectic manifold. The moduli space becomes a symplectic space, no longer a Poisson space. So finally, congratulations to Rhea and Eugene.